Good morning. Thank you so much for giving me the chance to talk about my work, and thanks for coming to hear about some of the neat things that we can do at MCN. I'm at Melbourne Uni, and if you look at the type of research I do, you might not think, where does nanofabrication fit in? Because I'm really interested in soft matter materials, interfacial phenomena, and for example, I care an awful lot about if I make an emulsion or a foam, whether or not it's going to be stable in a shampoo, in food, or breaking an emulsion and solvent extraction. So more particle technology, colloidal dispersions are a lot of the areas I work in. But a lot of the questions we try to answer, we do on a very fundamental basis. So we might be concerned if we, in a controlled manner, drive two drops together, what happens? If they collide, will they bounce off or will they stick together? And so what we've tended to do with MCN is not that we're necessarily fabricating a device to make it commercial, as much as fabricating devices to help us study soft matter and interfacial phenomena. And to me, this has been pretty exciting. One of our main tools is atomic force microscopy, which I'm sure most of you are familiar with for getting fantastic images, and we do a lot of imaging just as a matter of course or help others out, and those are just two examples of materials we've looked at. But really what has been fantastic about being at MCN is the ability to develop tools that help us study emulsions and foams. One very simple example, and we by no means invented this. This was out of the weights group. The pictures are ours, but the method's out of the weights group from actually quite a few years ago, about using capillary and capillary microfluidics to generate emulsions. And the reason why we care about this is just an example of how we've been able to use MCN. Is we actually use this type of microfluidic device simply because it's a great way to generate monodisperse emulsions. So a lot of the interactions we look at between drops and bubbles, and using some pretty fancy techniques I'll show you in a second, we also want to look at general emulsion behavior, and this is just a scalable way to make monodisperse emulsions. But really, one of the main tools we've used to look at the interactions between drops and bubbles, where our dropper bubble could be 100 microns in diameter or less, is using AFM. Now, not in the way most of you are familiar with AFM, it's a way to get pictures of a surface, but in this method we actually don't scan the tip around, but actually bring the tip of the AFM, which is a cantilever, down to a surface and look at the forces between those two surfaces. And we'll put a particle on the end of that cantilever, or in this picture, a drop. And that's really one of the biggest things we've done with MCN, is holding a drop or a bubble underwater on the end of an AFM cantilever is not an easy thing to do, and can be done commercially with commercial tips, but not very well. And so we were really fortunate to develop, in collaboration with MCN, a tipless cantilever that if we tried to get made from any of the commercial AFM companies, we're looking at $15,000 to $30,000 just to get them to develop it, whereas here we're able to collaboratively do it. And so the cantilever, I'm not going to go too much into the process other than say it's silicon on insulator, so we have to etch from both sides. But what's really key about this cantilever is at the end of it there's a clear circular patch, and that's just gold. And the rest of the cantilever is silicon. So it means using very simple chemical methods we can make that gold patch just hydrophobic. And so underwater the dropper bubble wants to sit there, and the rest of the surface the dropper bubble is repelled at. And as it turns out, these cantilevers are also very easy to stick large beads on, which is another way you measure forces. But we've even looked at possibly sticking cells on here to squash cells and look at cell adhesion. And so this is one more example of the things we've done with MCN. And this type of measurement, I'm not going to go into the details of what we've done, because this is just warming up to the example I want to show you today. We're able to get a front seat view when we drive two drops or bubbles together on how they interact on the scales of nanometers or microns. Now, why you would care about that is whether or not, if you formulated a shampoo, is it going to be stable? The same is true with food, and those are examples of, we've worked with personal care products companies and food companies, helping them look at formulations from a rather fundamental standpoint. One thing that when I first came down to MCN though that I realized was they had a set of characterization equipment, and this is kind of unique about a nanofab lab. The microfluidic fabrication was done on their wet lab. They have a fantastic wet lab facility to work with the nanofabrication side and the cleanroom side, and they happen to have a confocal microscope and an AFM sitting there, and we put the AFM on top of the confocal, and what that did was it helped us visualize our measurements with the AFM so we could see how far apart our drops are. And this was a really nice validation of a lot of the work and the theoretical analysis we developed for drops and bubbles. But instead of boring people with emulsions, because while I get really excited about them and I think molecules at that interface are fascinating and how that affects emulsion stability can be really engaging, maybe not to everyone this early in the morning. So what I wanted to do was give you an example of another way we've used some of the characterization and fabrication tools at MCN for something that's maybe a bit more applied. And this is looking at the problem in solvent extraction or pharmaceuticals where you can get drops that, or emulsions that you can't break. And particularly one of the problems is if you have clay in a solvent extraction circuit, it can coat your oil droplets and you get this clay armoring, or you get armored droplets where they're quite difficult to break. So we decided to make an oil droplet and cover it with clay, and then try to look at it mechanically to see what are the solution conditions that we might break this droplet at. And these are kaolinite clay platelets that we put onto oil droplets. The yellowish picture is just an optical microscope image of what that emulsion looks like. It's really polydispersed. We did that on purpose. The image down at the bottom which looks fantastic, although I have to admit the flaking out is probably because we didn't freeze it quite right. That's cryo-SEM, just to show what that clay structure looks like on a droplet. And what we're interested in is, are there solution conditions where we can break these capsules? Because that's a lot cheaper adding, say, salt or changing pH than putting these in a centrifuge, which is what has to get done in a processing sense. The actual measurement we did was we used those fancy cantilevers that I mentioned before, and we actually stuck a particle on the end of the cantilever instead of a drop, because we wanted a really big particle that we were going to use to squash our little capsule. And we're basically doing a micromechanical or nanomechanical load testing. So the same thing you might be familiar with large mechanical testing, macroscopic things like an instron or universal testing instrument, but we're scaling everything down to the size of the particles, maybe 10 microns. And we're squashing it maybe a micron or two, with a resolution and distance of a nanometer and a resolution and force of nanonewtons, even though this is on the scale of micronewtons. And what we did by combining this with an AFM with confocal microscopy was we were able to see how much we were compressing the capsule as we loaded it. And in an instron or a universal testing machine on a macroscopic scale, that's quite easy to do. But here's a little bit harder. And we had to use fluorescent dye in the oil. And we were literally, what we got out of it was how a load curve and the amount of strain we put on that capsule simultaneously. What you then do is you can take these images and use image extraction to generate profiles of that compression. This is not the easiest nanoscale measurement to do in the world. So fortunately what we did is there are other ways to figure out how much you've compressed a capsule like this. If you assume the drop's got a constant volume, from geometric arguments with the AFM, you can actually extract out what that profile should be for the geometry. And so that's the solid lines. And the dotted lines are what we actually extracted out from our image analysis. And this is a reasonable validation saying that we can do the measurement with a combined AFM and confocal, or we could actually do it just based on the geometry we knew we'd get out of the AFM. There's a couple assumptions there, so it validates them. Now, once you have a load versus strain curve, what do you do with it? Well, it's a mechanical test, so you have some type of micromechanical or elastic shell model to be able to pull out a quantity that's much more transportable. The thing we're pulling out is, in bold up here, it's the surface Young's modulus. And the reason why it's a surface Young's modulus, not say Young's modulus, which we'd be more familiar with from materials testing, is because we don't actually know the thickness of the clay layer. We have an approximate view, but in this instance, because it's quite a robust and complicated layer, we actually just pulled out we were able to scale for that with a surface modulus. It's a bit more forgiving, but on a relative scale, you can see how the modulus changes with strain. Modulus shouldn't change with strain, but Young's modulus, the surface modulus does. But the real thing is we looked at these capsules at different pHs, we looked at adding salt, and what we saw was there's no great difference in their modulus. But if we add surfactant, we can actually break the capsule, which was kind of exciting. Unfortunately, really what it meant was we were adding surfactant and solubilizing most of the clay, which does break the capsules down, and then the oil leaches out because the leftover coating is porous, but that's not terribly economical. So in the end we learned, wow, capsules are really hard to break. Now anyone that works in solvent extraction with particle contaminants, which they actually call crud problems, which is a great technical name, would already tell you that. But it's a way to try to develop those strategies. And one thing we accidentally did in the measurement was we had one capsule stick to our big bead, so we actually drove 2 capsules together, and this just demonstrates particle stabilized emulsions are really robust and very stable, and that's actually why they're so popular in other applications. So I hope what you can take away is, while we're not always making devices, we're making things, we're using MCN to help us study a lot of interesting fundamental science that does have applications that you might not have always thought of to come out of nanofabrication. And I'd like to thank my group that's worked down at MCN, Christine, Chris, and Srinivas, but there's also another Chris who wasn't working on this project, my collaborators from Melbourne Uni, and some of the other students that have worked on this project and moved on to more exciting things. So thanks for your attention.